Good morning, everybody. We're talking about section 3.2 today, and you definitely want to keep a calculator handy, graphing calculator handy. Again, if you don't have your own, you can go into Rapid Identity, and in Rapid Identity we have that nice little TI-84 Plus app, but I'm pretty sure almost everybody has their own. Maybe one person in pre-calculus doesn't. So some of the things that we're going to do today that I normally would do on the TV calculator for you, I'm probably just going to write those down so that we don't spend a whole lot of time with you watching me go back between my graphing calculator and the main screen. Because we've got a lot of numbers to go through as we talk about today and tomorrow's lesson with the objective of exponential and logistic modeling, where our goals will be able to model real life situations using exponential growth and decay. And definitely, that's what this is all about, you know. As we think about something as basic as a savings account, we want to experience how do you do that? How do you recognize that the correct math is taking place? And then find an exponential or logistic model for a real life situation using regression. That one we probably will have to wait until tomorrow. So the first piece that we see here says constant percentage rate and exponential functions. And when I see constant percentage rate, I think of a formula that you guys used in Algebra 2, which was it was called simple interest. And it was y equals a times 1 plus r to the t. And simple interest means you're earning interest each year, and it's at the exact same rate that it was the previous year. So this problem is exactly that setup. Suppose the initial population is 5,000 and it's growing 3% each year. Now, it's not money, it's people here, but it's growing 3% each year. Find the populations for the next 5 years. So we start with 5,000. But then we want to increase that by 3%. So if we want to increase it by 3%, we have to think, well, I want to keep what I have, which is 100%, plus I want that to go up by an additional 3%. So I really should multiply this by 1.03 to make that happen. And then we'd grab a calculator and multiply that out. And 5,000 times 1.03 would give us 5,150. Now the next year, we start over. And we say now we're not starting with 5,000. Now we're starting with 5,150. But the same thing is happening. We still want our original money back, which would be the 5,150, and we want an additional 3%. So we would have to take that once again times 1.03, and that would come out to 5304.5 or 0.50. Now, I'm leaving the decimals on here even though we're talking about population, and that's because I want you to see that we can get really accurate answers with these as we just keep going. So now I'd have to start off with 5304.50. And again, I would take that times 1.03. And we'd plug that into the calculator, and that would give us 5,463.635. Well, that's our new beginning for the fourth year. So 5,463.635 times 1.03. And that will give us 5,627.54405. And then that would be our new start at the end of 5 years. And we would again take that times 1.03, and we would get 5,796.372. So again, because of the sheer numbers that we're working with today, I'm not going to be plugging every one of these into that graphing calculator app that I have on the smartboard, just to save us a little time as we go through this. So it should become pretty obvious as we go through this that all we're doing is taking our answer and we're multiplying it by 1.03 one more time. You know, that's what's really happening here. And so we should start to get the feel that, hey, that would make this exponential, and the base would be 1.03. So going back to that formula that you used in Algebra 2, that makes perfect sense, because it would be 1 plus 3% would be 0.03 as a decimal, and that would make this the 1.03. And then A is what you start with, and what we started with was 5,000. So instead of continuing to do this recursively, and remember recursive is you use the last answer to get your next answer, we could have just popped this into this formula. But of course, the formula is going to change the look a little bit, and that's because that one is pretty generic. And since we're going to be talking specifically about populations quite a bit, what we would want to do is write a function that uses a capital P for population to tell people, hey, this is going to be a population model. So our exponential population model, if a population P is changing at a constant percentage rate R each year, then P of T equals P sub naught. Now that is still the initial amount. Remember, whenever we do the sub-zero, that means the null or the beginning population, whenever we have that sub-zero in there. And then we have our 1 plus R, where the 1 stands for the original 100% of whatever money you had in there or people that you started with for populations. And R is your interest rate as a decimal. And then T over here, that's going to end up being how many years this is going to happen for. So, reminder, again, last year's information, that if 1 plus R ends up being bigger than 1, that means we're trying to grow something. It's getting larger, just like it was in this example that we looked at up here. And so that's called a growth factor. And then if it actually goes down, if the population decreases, which does happen, this really becomes 1 plus a negative R, which would be 1 minus R. And we had a decay factor. So last year you had y equals a times 1 plus r to the t for anything that was growth, and then y equals a times 1 minus r to the t. So really all we're doing is just changing this, making it a little bit more generic so that we can have just one formula as we work through this. So growth and decay, again, just like you did in Algebra 2. So now we're jumping right in, sticking with that objective of we've got some applications modeling real life situations, and we want to use these. So example 1 says finding growth and decay rates. Tell whether the population model is an exponential growth function or exponential decay function, and find the constant percentage rate of growth or decay. So what we want to do when we see something like this is go immediately to that base and ask ourselves, well, is that a number that's bigger than 1? Because then they added the interest rate. And if, or in this case, the rate of growth. If it's less than 1, well, then it was decay. Well, this one's bigger than 1, so this is exponential growth. So that was the first thing they wanted us to do, was say, hey, exponential growth here. And then find, it says, the constant percentage rate of growth or decay. So I have to remember that this came from 1 plus r. Well, I think we can do this little bit of math in our head. Take the 1 off of there, and you have 0.0064. But we like to write those as percentages, and that's what it said right there. Find the constant percentage of growth or decay. And so we'd have to move the decimal 2 places to the right in order to talk about this as a percentage and make sure that we label it. So that would be actually let me put 0.64% for our percentage rate of growth or decay. And maybe just put a little comma here to break those two up. So there we have it. And again, this is something you did back in Algebra 2. So we get to B, which is Detroit, and we find out the base for Detroit. Hey, wait a second, that's not bigger than 1. So this one was actually decay. Detroit has been losing its population since the closing of a lot of the automobile manufacturers. So this is exponential. Decay. And then we have to figure out how much. So remember that this base came from, with our new model, it would have been 1 plus a negative r. But in this case, we could just say that's 1 minus r because that's decay. So if you wanted to figure it out algebraically, you could subtract 1 from both sides and then divide by a negative 1. But what most people will do is just say, well, if I take 1 and subtract 0.9858, won't that tell me what the difference is between those two? And it will. So if we take 1 minus 0.9858, and again, I'm not going to ask you to watch me punch that in. I'll just tell you what that was. That was 0.0142. So there's that. Now, again, that's our R value. But that's not talking in terms of percentages. So let's move the decimal over 2 places, 1, 2, and that would be 1.42%. So growth and decay, we have to be able to do that. We have to be able to take a look at it and say, hey, this is what I see. It's an exponential growth, an exponential decay model, and then figure out what was that percentage of either growth or decay. Example 2. Still working on real-life problems involving these situations. So determine the exponential function with an initial value of 12 increasing at a rate of 8% per year. So now let's go back to the formula that this book has for you, which is P of t equals, in fact, let me pop that back up so you can see for a second. The new model, P of t equals P sub naught times 1 plus r to the t. Or you could stick with the y equals a times 1 plus r to the t and y equals a times 1 minus r to the t. You don't have to start using the new model. It's just that this way our function notation tells somebody, hey, this is going to be population. All right, so we've got P of t equals an initial value of 12. There's the initial 100% with the 1 plus, and now we change that percentage of 8% into a decimal, which is 0.08. And this one just said determine the exponential function. So we don't know what the time is. We're just trying to come up with a model. Now we wouldn't leave it like that because we can all do 1 plus 0.08 in our heads, so we need to simplify that. But that's a fantastic model. So now if somebody wants to know the answer after 5 years, all they have to do is put a 5 in for t and get themselves the answer that they need. So this is just basic modeling that we've done so far of real-life situations. And now we want to look at some more detailed real-world problems that have to do with this. And it's exponential growth and decay model, so we're still sticking with that. But our objective of talking about the real-life situations needs to go a little bit farther than the money in the bank stuff that you did in Algebra 2. So exponential growth and decay models are used for populations of animals, bacteria, and even radioactive atoms. Any situation where the growth is proportional to the current size of the quantity being studied. And one of the big fields over the last 10 years has been forensics. You know, there's a lot of shows on TV about being forensic scientists, and so people have really gotten into this field. And we should just see a little bit of that to see if it's something, hey, are you interested in this? Is this what you want to do with your math experience as you get to thinking about college? All right, example 3, modeling bacteria growth. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. All right? So we're looking at a population of bacteria. And they said that it started at 100, but it's going to double every hour. Now, I don't want to overthink that. Doubling is 2. So it's going to be multiplied by 2 every hour. And I can just use T to stand for hours. So there's the model. Got a culture of 100 bacteria put into a petri dish, doubles every hour, and we want to predict when this comes out to 350,000. Well, that would be the population that would go on the left-hand side. Now, this one says, let's solve graphically. We'll review algebraic methods later in the chapter. So we're not supposed to say, oh, I'd divide by 100 and I'd take logarithms on both sides. What we're supposed to do instead is put it in the graphing calculator as y sub 1 and y sub 2. So that we can start to get a feel for the window. You know, what should we use for a window for a problem like this? So into the graphing calculator we go, and it was 100. Whoops, better get into the y equals piece there. 100 times 2 to the x. And we want to know when that will come out to be 350,000. Now, obviously, I can't use my negative 10 to 10 window. So back into the window here. And I remember that T is going to be the number of hours. Now, we know that it's doubling, so it's going to increase pretty fast. Maybe I'll try 0 to 20 hours. And then my Y values, I know that I have to be able to see 350,000, so maybe I'll put 360,000 on there. Just need to be a little bit higher. And then graph. And so that's a pretty good window. I mean, we can see that the growth is exponential there. We have that nice curve. And we can see exactly where they're hitting each other. So now we'll call it Blinky, second trace, number 5. And that is my first curve, my second curve, and enter. And there it is, 11.773 for x. So now I have to think x in this problem was really t, so it's time, and my label for time was hours. But if somebody went to all the trouble of calculating how long it was going to take for this to reach 350,000, there must be something important about that. You know, maybe the researcher that's in charge said, I want you to call me right away when we have 350,000 bacteria. So, might not be a good idea to leave that at 11.773 hours. We might want to figure out what that would be in hours and minutes so that we can make sure that we're going to be back in time. So, we'd have 11 hours, and then we could take that 0.773 times 60 minutes in an hour, and that would come out to about 46 minutes. So when the researcher says, all right, I want you to make sure you're here so that when we get to that 350,000 level, you're calling me right away so that I can do the next part of the experiment. And so we want to say, we want to interpret, you know, what is it that you would be able to say? And it would be the number of bacteria in the Petri dish will be 350,000 after approximately 11 hours and 46 minutes. Now, why not keep going and get hours, minutes, and seconds? Because real situations, biological situations, they're out of our control and they're never perfect. So sometime around 11 hours and 46 minutes, you'll be able to see the 350,000 bacteria in that Petri dish. Now, to myself, I'm thinking, this would have been so much faster to do algebraically just by, finding the logarithms and all of that. But like I said, the book wants us to hold off a little bit with doing too much with logarithms and just get used to figuring out the window, which is also a really good skill on our graphing calculator. So that was a big piece for real life. But we're not done with real life, so we have to keep going here. We have more knowledge that we can gain about this. And this one is exponential decay models model the amount of a radioactive substance present in a sample. And this is how, when you hear them say that they think the dinosaurs were around, X number of years, they're actually using radioactive decay to figure that out. The number of atoms of a specific element that change from a radioactive state to a non-radioactive state is a fixed fraction per unit of time. And that process is called radioactive decay. And the time it takes for half of the sample to change its state is the half-life of the radioactive substance. Now, decaying things is one of the key features of, things as basic as medications. When a medication has lost half of its potency, then that's when they say it's expired and you should toss it out. So that's how they end up getting those dates that you see on any jar of medication that you'll purchase, because it's going to lose half of its efficiency. All right, now example 4 says, let's look at this, because this, again, like I said, is a big field, forensic science. Modeling radioactive decay. Suppose the half-life of a certain radioactive substance is 20 days. Now that's really important. There are 5 grams present initially. That's another thing that's going to be really important. Find the time when there will be 1 gram of the substance remaining. Well, here's the first problem. This isn't happening every day, or every month, or every year. It's happening every 20 days. So what we have to do is figure out how the time interval is going to work here. And that's what this chart is for, to get us thinking about, what do I have to do if I know that this substance has been around for 100 days? What do I do? Well, let's think about this. If it were 10 days, that's not a full interval, because each one of those intervals of time is 20 days. But it wouldn't take us long to figure out that it's going to be 10 out of 20, which means we could use a half to figure out how many of those grams are going to be remaining as our time. Then when we see 20, we should be thinking, well, 20 is exactly 1 interval, because that's 20 days, and that's exactly what we had. 30 days is going to be 30 over 20, which would be 3 halves for a time interval. And then 40 would be 40 over 20, which would be 2. And I probably, for the people that aren't here, better write down that that was 20 out of 20. And then we'd have 50 out of 20, which would reduce to 5 halves. So now our job is to figure out those grams that are going to be remaining. And that means I want to think about my model. So when I think about my population of this radioactive substance here, and I will call it P of T, They did tell me what it started with. It started with 5. And they also told me what my base needs to be, because they said this is half-life. So a half of it is what's going to be my base. And what I just found was what I need to use for powers to figure out how many grams are going to be remaining after 10, 20, 30, 40, and 50 days. So I can start by taking 5 times a half to the 1/2 power, and that would give me 3.536 grams that are going to be remaining. And then 5 times 1/2 to the first power, which would of course be 2.5 grams. 5 times 1/2 to the 3/2 power is 1.768. 5 times 1/2 to the second power is going to be 1.25, which again makes sense. This was 1 half-life and this was 2 half-lives. So half of 5 was 2.5, half of that again is 1.25. And then 5 times 1/2 to the 5/2, 0.884 grams. So now, the reason I stopped writing my model was because I have to be able to figure out what should I be using right there for T. And each time that we did this chart, we ended up taking the number that we had for time in days and dividing it by 20, because that was the interval when a half-life was going to occur. So if I think of this generically, I need to take T and I need to divide it by 20. Because that's going to give me how many half-lives I'll have. That interval piece is so important for the time. So T divided by 20. Now we're not quite done. It said we want to know when there's 1 gram of that substance that's still remaining. So we need a 1 over here. And again, they did want us to solve this one graphically. So we'll go ahead and get that in the graphing calculator. So this was our 5 times the quantity 1/2 to the, and then I'll need some parentheses up here, and that's going to be our x divided by 20. For our power. We want to know when is that going to hit 1. So now, window. We have hours that we're looking at, and we already know by the time we get to 50, we're down to 0.884 from looking at our charts. So 0 to 50, ought to be able to do that. And this started at a measly little 5 grams. So let's go ahead and have our y's be at 0 to 5. Well, there it is. And we can see the intersection of the two. So second trace, number 5, enter, enter, enter. 46.439. Now, this information was all given in days. And the question actually said, find the time when there will be 1 gram of a substance remaining. So we could put this into days and hours and make it a little bit more accurate. It won't be wrong to leave it as 46.439 days. But again, apparently somebody really wanted to know when this was going to be down to 1 gram. So we better take our decimal, which is approximately that 4.439. And since this was in days, and we know there are 24 hours in a day, we could take 0.439 times 24, and that would give us about 11 hours. So again, we want to interpret this. We want to just make a short sentence saying, hey, this is what we found. there will be 1 gram of the substance, because they didn't tell us what it was. So there will be 1 gram of the substance in approximately 46 days and 11 hours. Now, the word that's really important for us here is going to be the approximately, because again, you know, this is something that's out of our control. It is a biological substance. It's probably not going to be exactly 46 days and 11 hours, and we know that because we had to do some rounding here, but also because, you know, things don't work out perfect when you run your experiments. So I think the only really challenging piece about this problem is figuring out what you have to use for time up here, and the realization that we have to know how many of those 20-day intervals have passed. And that's what we're going to focus on for a little bit here, is the skill of figuring out, you know, what do you use for your exponent. So scientists have established that atmospheric pressure at sea level is 14.7 pounds per square inch, and the pressure is reduced by half for each 3.6 miles above sea level. For example, the pressure 3.6 miles above sea level is half of 14.7, which is 7.35 pounds per square inch. This rule for atmospheric pressure holds for altitudes up to 50 miles above sea level, though the context is different. The mathematics of atmospheric pressure closely resembles the mathematics of radioactive decay. So it's a lot like half-life is what they're saying. It's very similar to that. Now, for example 5, determining altitude from atmospheric pressure. Find the altitude above sea level at which the atmospheric pressure is 4 pounds per square inch. So, I don't think I'm going to use T this time because this isn't about time. It's actually about altitude, which is height. So I think I'll use P of H. It started at 14.7, but it's just like half-life, decreasing by a half for each time interval. So now what I really have to spend time on is, instead of time interval, what's this height business that changes this interval? It's reduced by a half for every 3.6 miles above sea level. So I start thinking, okay, so that means if I have perfectly 3.6 above sea level, that's going to be 1 time increment. But if I had 7.2, that would be 2 time increments. So what am I doing with those numbers in order to figure out how many intervals there are? And it's exactly the same as our radioactive substance, except that now it's 3.6. So I'm going to have to take my height and divide it by 3.6 to figure out how many of those increments do I have. And again, they wanted us to figure out a specific pressure, which was 4 pounds per square inch. So we need to punch in a 4, almost looks like a Y over there, make it a little crisper. There we are. So Y sub 1 and Y sub 2, and set the window so we can see what we need to see. Alrighty, so it was 14.7, parentheses 1/2, parentheses, to the parentheses, and we needed H or X divided by 3.6. Kick it out, and we want to see a 4. So, window time. Well, we're talking about the height, and this is the height above sea level. So, I don't know, we'll just pick something and go with it. Let's try maybe 0 to 20. And I have to be able to see 4, so maybe 5 would be good enough. Let's give it a try. And then we can change it. Oh, nope, that's going to work. I can see it. So second trace, number 5, enter, enter, enter. And there it is, we're going to have to do 6.760 with our rounding to 3 decimal places. And then we want to figure out a label for that. And that was in, scroll it back so you can see it here, miles above sea level. So our interpretation, the atmospheric pressure of 4 pounds per square inch can be reached, forgot the C in reached, at approximately 6.760 miles, and then we want to make sure that we're putting above sea level because that was part of the problem up there, above sea level. Now with that one, the 6.760 in miles, nautically, they're probably not going to care if you change that into miles and feet. And that, again, is going to be because, you know, most of the world is going to use this in metrics, but we are using miles and feet. So you're probably better with this one just sticking with the 6.760 miles. And again, none of the answers that we've done have been wrong. We're just writing them a little bit more detailed and a little more accurately, specific to the situation, you know. If you're talking about the medical field and they wanted to know when we had 350,000 bacteria, that's probably something that's really big and they want to know it right away when that happens. But with this, this is probably more than enough information for them to get their 4 pounds per square inch. Well, what's up with the blank page? Alrighty, so you'll notice here, because this changes, these problems that involve time are going to change every year as the year passes, that I wrote 2021, and let's assume that they used census data on these problems because these are about population. So tell whether each of the population models is exponential growth or exponential decay. Find the growth and decay rates and factors for each. Use the model to predict the current population. Now, another thing you're going to notice is that you don't have these little red 0.5s on your papers, and that's because I wanted to make sure that we talked about that. Remember, with census data, that's collected halfway through the year. So when our time equals 0 says 1990, it's really 1990.5. It's been half of the year for that census data for both of these. So I would like you to go ahead and tell whether or not these are exponential growth or decay, and then give me the percentage rate of growth or decay, and then we'll come back together and we'll do the rest of the problem. All right, 1A, I'd like somebody to unmute and tell me if this was exponential growth or decay. It is growth. And what would our R value be before we change it into a percentage? Thank you.
0.0136.
Good, good. So then we'll change that into a percentage. And then we'll just go on to B, and then we'll come back and do the rest of the problem that they want here. So somebody else, tell me about B, growth or decay, please. Yeah, that one's decay. And did you find R?
0.0142.
Thank you. So we'll move it over 2 places. And that'll be 1.42%. All right, now, like I said, we'll come back together to do the second part here. And that's because they've got the model for me. So what is it here they're asking me to do? Use the model to predict the current population. And that's why I said we're definitely going to use 2021 for this one, because T, it says, represents that year 1990.5. Well, if I'm going to use this model, I have to know how long ago that was. So I'm going to have to take 2021 minus 1990.5 to figure out what I have to use for T, and that's going to be 30.5. Now we'll have everything we need. P of 30.5 is what we want to find. Oops, that got squashed. And we would plop that in the calculator. And because this one is a population model and we're assuming, of course, that it's people, we would want to round this to the nearest whole number. So I'm not going to waste your time making you watch me type that in. So we've got 1,181,070 people. So 2 things that were really key with this problem. We had to remember that census data gives us that additional little 0.5 piece on there. And we needed to be able to figure out, hey, is this growth or decay? Then, similar situation for Detroit, except their population is going down. So I'd have to take 2021 minus 1980.5 to figure out how many years have passed, and that's 40.5. And then put that into the model. If I can fit that in there as the 40.5 power up there, and punch that in. And again, not going to waste your time making me watch that, punch that in. That's 674,288 people. So, whether or not it's growth or it's decay, they gave us the formulas. Our job is to think, all right, this is census data. How do I get the right amount of years that I need to make sure that I can give them a current population? Number 2 switches gears from population to talking about population of bacteria. So, a small culture of 10 bacteria is placed into a petri dish. If the culture doubles every hour, after how many hours will the number of bacteria reach 500,000? Well, let's get a model first. We know it only started with 10, but here's the important piece. It's going to double every hour. Now, then I want to take note of the fact that if I put a T up there, that T stands for hours, just in case somebody tries to change it up on us with the label. So then you go back and you take a quick peek and you see after how many hours will the bacteria reach 500,000? Well, that's exactly what we're doing. So we want to know when is this going to happen? So again, they really wanted us to go ahead and plug this into the graphing calculator, but I think it's important at this point that we start to get a feel for how logarithms would work in a situation like this. So I would divide both sides by 10, and of course that's going to take one of these zeros off of here. And then to get rid of that base of 2, I can take the logarithm base 2 of both sides. Now, we don't have a logarithm base 2 on our calculator, so we're going to have to use the change of base formula. And the change of base formula says take the logarithm of the big number over the logarithm of the small number for the base, and you'll be able to get that change of base formula to give you the correct answer. So we have 2 buttons we can push for logarithms on our graphing calculator, and that's going to be either log for logarithm base 10 or ln for natural logarithm. In calculus, you use ln a lot more. So let's go ahead and use natural log of 50,000 divided by natural log of 2. And over here, because the base of the logarithm and the base of our unknown power are the same, they're inverses, and they just drop right out. So we'd punch in the natural log of 50,000 divided by the natural log of 2, and that would give us 15.610 hours. Again, somebody specifically wanted to know when are there 500,000 of these, so we could take the 0.610 times 60 to figure out how many minutes that would be, and that comes out to about 37 minutes. So we could tell them 15 hours and 37 minutes. And we'd be a little bit more specific with what we have going on. Problem 3, still talking about Petri dishes here. What if the initial bacteria in example 2, so same amount that you started with, but now it triples every hour? Oh, well that's not a big change. And T is still going to be in hours. How many hours would it take to reach that 500,000? Well, obviously we're going to expect that to be less. But we realize the only thing that's changing here is that base is 3. So we'd still divide both sides by 10 and get 50,000 over here. And then we'd have that 3t, 3 to the t, I should say. And then we'll take the logarithm base 3 of both sides. And we'll use natural logarithms for our change of base formula. So we'll be punching in the natural log of 50,000 divided by the natural log of 3, and that will come out to 9.849 hours. Now, if we wanted to know specifics again, we would take our little 0.849, move this down, can't take it without the other one, times 60, and we could get that into minutes, and that will be about 51 minutes. So 9 hours, 51 minutes. Now, my little timer just went off, which means we only had a minute left here. And we didn't finish up. I had hoped for us to be able to get through the back page. That was one of the reasons that I didn't punch absolutely everything in here. But I'm pretty sure you'll still be able to do the assignment. We just might run into needing about 2.5 days for this one instead of 2 days like it's on the calendar. But we'll just steal a little bit of time from 3.3 when we get there. Oh, I hope that's not. Here, let me move that down. It's probably right in the glare spot there. But section 3.2 day 1 homework is 1 to 13 the odd, and then 15 to 22, and 29 to 34.